Okay, so good afternoon to you all. I'll be filling in for Moshe, who's my PhD student, and of course he did all the work here, so I want to give him all the credit. This is work that was carried out in collaboration with Roy Day-Stirrat and Macaulay at Shale in Houston. So when we think of mechanical properties of shales and how this relates to fracking, it's pretty obvious that the fracking process itself is a mechanical process and is determined by the mechanical properties of the rocks. But also production and the way production changes might also be impacted by the mechanical properties as well. So, of course, if you want to understand the different stages of gas production from shales, we're going to have to understand a little bit more about their mechanical properties. So, just to take you back to high school, here we have a stress-strain curve here that I'm sure we're all familiar with. There are two main regions and a point here that are important. There's the elastic region, where the sample or the rock will deform elastically, like a spring. Then we get, of course, the plastic deformation, and eventually the rock will fracture. Now, of course, if we want to understand the way the full regime, the way the rock will behave under these different conditions, we're not just interested in the fracture and how it breaks. We're going to be interested, and what we're going to focus on in this particular talk is are the factors that influence the elastic properties and the elastic behavior of the rocks, and that's at different scales. So when I talk about different scales, when you look at a typical shale, I think most of us will agree that they're quite uninspiring. They're quite dull and grey, and they don't really tell us very much. I think one of the interesting things is about shales is when you start zooming into different scales, and particularly at high magnification. And here you can see a scanning electron microscope image of a pretty typical shale. And here the bright white regions, that's pyrite, and you can see they make up those pyrite framboids, which they aggregate together. We can also see here larger grains as well. Do I have a pointer here? Okay. You can see these larger grains that are possibly calcite, possibly quartz grains. And then, of course, we see these kind of linear elements, and those are the clay minerals. One of the interesting things is that we can actually see that there are all kinds of shapes in this image. We can also see here, most importantly, for this talk at least, is the dark regions. Now, the dark regions are the organic matter. And we can see here that basically it's quite a complex image. These are not simple spheres. These are not simple geometries. We've got quite a complex image and filled with various different materials with different mechanical properties. Now, one of the interesting things is, or one of the ideas that has been, floated, is the idea that if we knew the mechanical properties of all the different components in the shale, we could then kind of build either a finite element model and then reconstruct the bulk properties. Now, of course, that's a pretty. It can be useful, but of course it's a naive approach. I think if we're going to scale up from this scale to a larger scale, of course we're going to get different mechanical properties. But I think the very fact that the model will fail, even when we start inputting all these different all these different data into the model, the very fact that the models will fail, and I'm pretty sure they will probably tell us about the different factors, the different mechanisms that are controlling the mechanical properties at different scales, which in itself is an interesting point. So what we're going to talk about today is trying to extract information on the mechanical properties of the shales at the much finer scale. Now, if we zoom in a little bit further, and this here we can see the field is about I think 6 or 7 microns across, and we can see here the black regions are the organic matter, and we can see here this big chunk in the middle that's a couple of microns across. It's got a pore in the middle. But we can actually see that a lot of the organic matter actually fills the voids in between the clay minerals. Okay, so all the black streaks here are basically organic matter filling the voids in between the clay minerals. So one of the kind of obvious points that comes out of this is that much of the organic matter in shales, it does fill these larger micron scale voids, but it also fills nanoscale voids in itself. Not only does it contain nanoscale voids, but it actually fills nanoscale voids. So one of the problems with this, or one of the problems that this presents to people trying to measure mechanical properties, is that standard techniques, for example, nano-indentation, micro-indentation, just basically mean we cannot measure the mechanical properties of these smaller, the organic matter in these smaller voids. We don't know if that's going to be important or not. These standard methods have poor spatial resolution, and more importantly, they're destructive. If I measure once, I can't go back to the same point and measure again because I've destroyed the point that I've measured. So that basically leads us to the objectives of my research, or Moshe's research, and what we'll be focusing on today is this first point, and that's developing a method to map elastic moduli in with a non-destructive technique, and mapping it with actual nanometer scale resolution. Then the next stage is going to be looking at the effects of thermal maturation. We're already doing that, but I won't be presenting the results today. And we're also going to look at in situ heating, and that's taking advantage of the fact that these measurements are non-destructive. So, and of course, the last kind of longer term is trying to integrate our measurements with models and trying to upscale them to see what happens at the larger scale. So, for those of you who want more information, I'll just be skimming over the main results of this paper that's just coming out now in Marine and Petroleum Geology. And here there's a lot more detail about the method and about what we did. So just for those of you who aren't familiar with atomic force microscopy, and this is the method, this is the main instrument that we'll be using, atomic force microscopy basically scans over the surface of a sample with a very sharp needle. Now, usually people use the topographic mode, so basically you can reconstruct the topography of the surface at the with nanoscale resolution. What we're actually using is another mode, an additional mode that you can actually get out of this scan, which is you can actually get the mechanical properties. And by mechanical properties, I mean the Young's modulus of the actual sample. So here you can see this is a typical shale sample. The splotches, or the bright points, the stars, if you like, are the pyrite grains. You can see here, these lines are actually the argon mill that we use to polish up the sample. And this is the tip. So if we're looking from an optical microscope point of view, looking down along the sample. Okay, so this is basically scratching the surface, feeling the surface, and telling us the topography and the mechanical properties at the nanoscale. So what are we actually getting? For each pixel, we get a force distance curve. Okay, so basically, as the tip approaches the surface, we're applying a certain force, and we can actually fit a DMT modulus curve to each individual pixel and extract the Young's modulus. There are a few things we have to know, or we should know better. For example, the Poisson's ratio of the material that we're measuring. But all in all, we basically get a Young's modulus for each pixel. Now, if I'm working at 512 by 512 resolution, I get for each image more than 260,000 modulus measurements, which gives us a fantastic ability to characterize the sample with quite good statistics. And I can afford to be very critical of the data. So just a little bit more about the methodology. We take our shale samples, we argon mill them to get a very smooth nanoscale go We then look at the surface with electron microscopy to identify regions of interest. We then go back to the atomic force microscope and then map those regions of interest. And often we have a bit of a go backwards and forwards between electron microscopy and the AFM, getting better and better images. So what I'm going to be showing you today is results from rocks that they're basically thermally mature with type 2, type 3 kerogen source rocks, and they're in the dry gas window. So we're talking about very, very mature rocks. So this is a scanning electron microscopy image of a region. You can see here this is a quartz grain. We see here the framboids. We can see here there's not that much organic matter. That's the black points here. What we can also see, there are also calcite grains in this image. You can also see here when we look at the atomic force microscopy, the topography channel of that same area, we don't see very much. We see this kind of grain peeking through here. We don't actually see very much in terms of the surface expression of the mineralogy. When we use another mode that's related to the topography, it's kind of it's like shining a light on the surface So it kind of gives us a pseudo 3D image. Suddenly we see a few more grains popping out, but again, we don't see very much. However, when we pop to the Young's modulus map, suddenly we actually see the individual grains, and we can identify four main modes here. So we can see here the light blue, which are the mineral grains like calcite and quartz. We can see here the dark blue, which is a kind of mixed aggregate of organic matter and shales, and clay minerals. We can also actually see these bright pink regions, which are the very stiff pyrite, which comes out. And then there's the green, which is the organic matter itself. And there's a very good correspondence between the green and the black in the SEM images and the Young's modulus. So just to show you the other kinds of things that we've been doing to kind of verify what it is we're actually imaging, we've also been doing EDS. So we can see here this verifies that it's these are silicon grains. We can also see here carbonate grains in some of the regions here. And we can also see the pyrite. Okay, and also the carbon map gives us also a pretty good confirmation that we're talking about organic material. So basically, what are we doing? We're identifying soft intergranular organic phase, which is somewhere between 0 and 25. And this isn't because we're getting poor measurements. It's because we're actually getting a distribution of values. Okay, so this is the electron microscopy image. This is nanomechanical imaging, and those are basically imaged with two different instruments. Okay, so we also get the clay matrix, which is kind of clay minerals, probably mixed with organic matter, and we're getting somewhere between 25 and 40 GPa. We're getting isolated grains, which are a little bit low here, somewhere in the 40 and 80 GPa range. And we also get a minor mineral phase, pyrite. And these are all phases that we can identify using the atomic force microscopy. So just to give you an idea, these are the kinds of things that we can do. We can build these statistical characterization of the mechanical properties. Okay, so we're getting a frequency here, Young's modulus along the x-axis. And if we zoom into regions of interest, for example, this red region, we can see here that's the mechanical properties of that particular window. And we can see here the organic matter just jumps out here at around 5 or 6 GPa. And basically what we're seeing, though, is that for this particular sample, we were seeing peaks mainly around 15 to 16 GPa and additional peaks at the smaller than 10 GPa. So just to run ahead, we want to also look at thermal maturation. We were looking here in this particular window of very high maturation. We were going to look at samples that are, or we were already looking at samples that are in the lower maturation range. We also want to look at the effect of temperature, so we can actually heat up the sample and map and image the surface as the temperature changes and see the effect on the modulus. So these are the conclusions. Basically, PeakForce QNM, which is the method that we've been using, is a powerful tool for characterizing the surface. These are the values we got for a thermally mature source rock, 15 to 16 GPa for the organic matter, and additional peaks at below 10. And I think I've used up all my time. Thank you.
Thank you. Again, we have time for one question as we switch over speakers.
My one quick question.
Yes.
Any success in upscaling right now? Have you tried looking at those maps,
I mean,
some average, and then in stress cell experiments comparing that to...
Okay, so we get an average. I mean, at the moment, though, we haven't actually compared that average with the values that we get. But I also think it's not, it might be, it's very naive just to take an average value and then kind of plug it in, and then, because that's not going to work. So we haven't then tried to use those. And one of the steps would be to then use the values that we get into some kind of finite element model and see what happens. So.
Thank you very much.
Okay, our next speaker is...